How do emissivity and absorptivity affect radiation heat transfer? Imagine standing near a campfire and feeling the warmth on your face. That heat reaches you through radiation, which is a way surfaces exchange thermal energy. Now, the way surfaces emit and absorb this heat depends on two key properties: emissivity and absorptivity. These properties are like the surface's personality when it comes to heat. Emissivity tells us how well a surface radiates heat compared to a perfect black surface. A black surface with an emissivity of 1 emits the maximum possible heat at a given temperature. If the surface has low emissivity, it emits less heat and tends to reflect more radiation instead. Think of it like a mirror that reflects most of the heat instead of giving off its own. Absorptivity, on the other hand, measures how much incoming radiation a surface can absorb. It also ranges from 0 to 1. If a surface has high absorptivity, it absorbs most of the radiation that hits it. According to Kirchhoff's law of thermal radiation, for a surface in thermal equilibrium, the absorptivity equals the emissivity at each wavelength and direction. That means if a surface absorbs radiation well, it also emits radiation efficiently. When it comes to heat transfer, these properties control how much energy a surface gains or loses through radiation. Surfaces with high emissivity and absorptivity will absorb more heat from their surroundings and emit more heat themselves. This increases the rate of radiative heat transfer. Conversely, surfaces with low values for both tend to reflect more radiation and emit less, reducing heat exchange. The Stefan-Boltzmann law helps us understand this better. It states that the power radiated from a surface is proportional to its emissivity times the Stefan-Boltzmann constant times the surface area times the temperature to the fourth power. So, if the emissivity is lower, the surface emits less heat at the same temperature. In real-world applications, controlling these properties is very important. For example, high emissivity coatings are used on radiators and heat exchangers to maximize heat rejection. Reflective surfaces like aluminum foil are used in building insulation to reduce heat gain by reflecting radiation. Surface treatments like polishing or oxidation change emissivity and absorptivity, which directly impacts how much heat is transferred. For instance, oxidized metals tend to have higher emissivity than polished metals. This means they radiate heat more effectively. In summary, emissivity and absorptivity are fundamental in determining how surfaces exchange heat through radiation. Their values influence the efficiency of heating and cooling systems, making them essential considerations in design and analysis of thermal systems.